Welcome to Lecture 3.2, Equations with Constant Coefficients. In this lecture, we will learn how to solve a special class of linear second-order ODEs. Recall that an equation is linear in second order if it has this form, and is homogeneous if this last term, forcing term, is 0. So, as we did with first-order ODEs, and as we mentioned in the previous lecture, we will always solve the related homogeneous equation first, meaning we will, even if this is not 0, we will make it 0 and solve that first. But to start, in this lecture, we will only consider homogeneous ODEs, and moreover, we will only consider ODEs where these functions are actually constant. And that may seem like it's a big restriction, but it actually comes up in a lot of situations. Like, recall the mass spring systems. There we had mu was the constant here and k was the constant here. So in a lot of ODEs that come up, these things are constants to begin with. For these equations, there will be a two-parameter family general solution, something like this, c1y1 plus c2y2. So the goal, knowing that there is a two-parameter family of solutions always, is to find these two parameters. To find a y1 and a y2, that solve the ODE, and then we know that we're done. So we'll start with some simple equations, ones where we can actually see y1 and y2 by inspection. So first, consider this ODE, y double prime equals k squared y. And let me ask you, can you think of a function y1 of t such that its second derivative is equal to the same function except a constant pulls down, a positive constant pulls down? So maybe you're thinking of an exponential function. So y1, in other words, y1 of t is e to the kt. Notice that when you take two derivatives of this function, let's actually do that. So y1 double prime, what is that? That is equal to, well, each derivative, a k pulls down and you get the same thing back. So y double prime is k squared e, can't get my pencil to work, e to the kt, and that's just k squared times y1. So yes, this works. What else would work? How about a y2? Now it's tempting. It's tempting to say something like, well, what about y2 of t to be 2e to the kt? But we're not going to count that as being different. We actually need two different functions, y1 and y2, for this to work, because we have a two-parameter family of solutions. And this function is already in the family of solutions c1, y1, because it's 2 times y1. So we're not going to let this count for our second solution. So what else is there? Well, here's something that you might think of as well, y2 of t. What about e to the negative kt, right? What happens if you take two derivatives of this guy? Well, each derivative, a negative k pulls down, so when you take two derivatives, you get a positive k squared pulling down. So these are two truly distinct solutions. One of them is not a scalar multiple of the other. And so we have two distinct solutions, so we have our general solution like this. In other words, y of t is c1 times y1, so c1 e to the kt plus c2 e to the negative kt. Here, that's supposed to be a t, this is our general solution. Let's do our second example. Find the general solution to this equation. And the reason why we have a k squared here instead of just a k is because we want to emphasize that this is a negative constant. So what function, can you come up with a function whose second derivative, when you take its second derivative, you get back the same function up to some sign and a constant. So you take two derivatives, you get the same thing back, but the sign flips. What does that remind you of? How about cosine and sine? So let's check. y1 of t is cosine of kt. Well, let's take two derivatives of this. When you take one derivative, the first derivative, a negative k pulls out, and you get, let's just write it down, y1 prime is k sine of kt, and I think we need a negative sign here, right? Yeah. And then y1 double prime, now you just get a k out, and so we get negative k squared cosine of kt. And notice that this is just y2. Oh, yeah, this is y1, not y2. Sorry. And so this is negative k squared y1. So similarly, it's easy to check that another solution is sine of kt. So our general solution is y of t is c1 cosine of kt plus c2 sine of kt, and that is so every solution to this equation by our general theory can be written like this, some linear combination of sine and cosine waves. Now, one question that I sometimes get in an in-class lecture at this point is, why doesn't this equation solve this ODE? Doesn't this also work? So think about it a moment and think why I claim this does not solve this equation. And the negative sign can throw you off, but this solution to this equation, when you take two derivatives, a negative k squared pulls out. And when you take two derivatives of this, you get a negative k times a negative k, which is a positive k squared. So this solves that equation, but not that one. Okay, so let's do a more complicated example. And recall in this section, and actually most of this chapter, we're only going to be considering equations where the coefficients are constants, as they are in this case. So the game is the same as in the two previous examples. We need to find some y1 and y2 that are solutions, and then we have our general solution. But in this one, it's not exactly clear how to begin looking for a y1 and y2. So I'll get you started. So let's try a function like this. Y of t equals e to the rt. Now this probably seems like it comes out of left field for most of you. So I'll take a minute or so to explain why this actually makes sense and why this is going to work in general. So of course the goal, as it is in so many of these problems, is to guess, well, given a good guess for a solution, figure out what unknown parameter works. So find r. So let's take a moment to understand why this is a good guess. So notice that the derivatives, y prime is r e to the rt, and y double prime is r squared e to the rt. And let's imagine, before we do it, what happens if we plug these guys into the left-hand side of this equation. So each one of these terms, y double prime, 3y prime, or negative 3y prime, and 2y, each of these is some number of e to the rt's. So if we plug this thing back in, we can factor out an e to the rt, and then we can solve, so some number of e to the rt's equals 0, so let's solve for that expression in R. If you didn't catch all that, let's do that. So let's plug back into the start equation. Okay, so y double prime is going to be, see, that's r squared e to the rt minus 3 times r prime is this, 3 times r e to the rt plus 2 times y, which is 2 times that guy, so 2 times e to the rt equals 0. So when we plug it back in, we get this equation, and now we're going to factor out e to the rt. So we get e to the rt times r squared minus 3r plus 2 equals 0. So in other words, this left-hand side is 0. Equivalently, this is a solution if and only if this equals 0. So we have a solution of the form e to the rt for each root of this polynomial. So this function, this non-zero function, times this number is 0, we can just divide through by this function and look for when this is 0. So we factor this and we get r, how does this factor as? R minus 1 times r minus 2, yeah, equals 0, which means that r equals 1 or 2. That means is we have two solutions. So we have two solutions. y1 of t equals e to the 1 times t, or e to the t, and y2 of t equals e to the 2t. In other words, both 1 and 2 are exponents that give us a solution. And this means we found the general solution, because that's all we need, are two distinct solutions that are not scalar multiples of each other. So the general solution is y of t is c1 y1 plus c2 y2. So c1 e to the t plus c2 e to the 2t. So here is our general solution. And now you can think about it that if the fact that this is 3 and negative 3 and 2, for any other constants, something like this should work. We could guess a solution of the form e to the rt, and when we plug it back in, we get a polynomial in R, which, unless we're really unlucky, has 2 roots, and that gives us 2 solutions, and hence our general solution. Okay, let's do another example. Find the general solution to this equation. So let's do what we did before. Try y of t is e. So guess there's a solution of this form, and we want to plug this thing back in and solve. So y prime of t is r e to the rt. Y double prime of t equals r squared e to the rt. So we plug this thing back in, and we get, so y double prime is r squared e to the rt minus 6 y prime, that's minus 6 times r e to the rt, r e to the rt, plus 9 times y e to the RT equals 0. So we factor out e to the RT, and look what we get. We get x squared minus 6r plus 9 equals 0. Now you may be noticing a pattern that this is called the characteristic polynomial. Let me actually write that down. This is the sometimes called the characteristic. Oh no, I didn't spell that right. Characteristic polynomial. And that's doesn't take long to see why that's always going to have the same coefficients as these coefficients here. 1, negative 6, 9, 1, negative 6, 9. So you can actually take a little bit of a shortcut and just, for all of these, write this. You can start here and write this as e to the RT times this is 0, and then you can divide through by that because that's this function is always non-zero. So a non-zero function times a number is identically 0, better mean that number is 0. So in this case, we factor this, and we get that, you see this factors as r minus 3 squared is 0. So what does that mean? That means that we have a solution. So we have y1 of t is e to the 3t. That is a solution. So this is a solution. Unfortunately, we're looking for two solutions. If we want the general solution, we know that there are, our theory tells us that there's a two-parameter family of solutions, and unfortunately, we've only found one. So we need to somehow, so let me write that down. We need one more solution. We need one more solution. So how do we find it? Again, it's also not clear where to go from here, but I'll tell you something which always works is try. So we need a solution. Let's look for one like this, y of t. Let's look for something that's a little more complicated than e to the 3t. So how about something of the form v of t times e to the 3t. Now, we know there's a solution when v of t equals 1, or any constant for that matter, but let's see if we can find a slightly more complicated v of t, like maybe a first-degree polynomial. And it turns out that this will always work. So try this and solve for v of t. Okay, so before we can do that, we have to take the derivatives. We got to plug this back into here, so we got to take the derivatives. So y prime is, so let's write this as y equals v e to the 3t. We're going to suppress our of t's. So y prime, we got to use the product rule, is 3 e to the 3t times v plus e to the 3t times v prime, using the product rule. And then y double prime. So let's see, y double prime is 3 times the derivative of, well, we know the derivative of what I'm circling here. That's just this whole thing. So that's 3. Oh, let's get my pencil back. That's 3 times 3e to the 3t v plus e to the 3t v prime plus, now we got to take the derivative of this, also using the product rule. So plus 3e to the 3t times v prime plus e to the 3t times v double prime. And again, that's just the product rule. So simplifying terms, we see that this and this add together. So we have 3 times this plus that. So in other words, simplifying terms, we get 9 e to the 3t times v. That's 3 times this. Okay, so how many v primes do we have? We have 3 from here and 3 from here. So we have plus 6 e to the 3t v prime. And then how many v double primes do we have? We have, we just have one of them. We have 1 times e to the 3t plus e to the 3t v double prime. And now let's factor out. Well, actually, let's not factor it out just yet. We don't. So what do we need to do? So we said that we are going to be plugging this thing. We're plugging y into our ODE. So we have to plug. So yeah, let's do that. So let's plug in. So plug in. So y double prime, that's this term, is this thing here. So plug in, we have 9 e to the 3t v plus 6 e to the 3t times v prime plus e to the 3t v double prime. This is our y double prime. So minus 6 times y prime. So let's subtract 6 of these. Minus 6 times 3 e to the 3t v plus e to the 3t v prime, and plus 9y, y is just v times e to the 3t, plus 9 e to the 3t. This all equals 0. So again, this is y double prime, this is negative 6y prime, and this is 9y. So, oh, hold on, I forgot my v right here. V. So what do we notice? First of all, we can divide through by e to the 3t. Actually, well, let's collect terms. So we have. So how many v's do we have? We have 9 e to the 3t v over here. We have 9 over here, and then we have negative 18 right here. So those all cancel. 9, 9, and negative 18. Okay, what else do we have? We have, how many v primes do we have? We have 6 v primes here. We have negative 6, well, 6 e to the 3t v primes here, and negative 6 e to the 3t v primes here. Those will cancel. And we are left with, so all we're left with now is e to the 3t v double prime equals 0. And you may be wondering, does this always cancel like this? And the answer is yes. And that's, go back and check, but that is precisely why we chose something like v e to the 3t. It works. It should not be clear by looking at it why it works, but trust me, it does. And if you don't believe me, you are always welcome to take these steps and check. And actually, it's worth doing it, because if you take these steps and you don't get something that massively cancels, that should be a red flag that you've probably made a mistake. Okay, so here's what we have. We have this. Now what does this tell us? So this is a function, and that's a function, and it's the zero. So this function is the zero function. And this is certainly not, it's not zero anywhere, and it's certainly not zero everywhere. So if some non-zero function times a mystery function is zero, then that mystery function better be zero. So that tells us that v double prime is zero. So what functions, okay, so what does v have to be? If its second derivative is equal to zero, well, what function satisfies that? Well, a linear function. So that means that v of t has to be mx plus b. Right? I'm going to write this as actually ct plus d. So any, and I stress any function of this form, cd plus d, is going to work for a solution like this. So you're free to choose any c and any d that you want. Well, almost any. Now, if you remember what we're doing. We have one solution. We're looking for another solution. y2 of t. This is what we're trying to find, a second solution. So here we have a two-parameter family of second solutions. 1t plus 1 works. 18t plus 3 pi, that works. We only need one. So let's come up with the simplest solution we can from this. Well, not quite the simplest, because if we pick c and d to be 0, that doesn't help us. Or if we pick c to be 0 and d to be 1, then we get the same solution that we got here. And we actually want, remember, a different solution. So let's pick the simplest non-dumb example, and let's let c be 1 and d be 0. So that will give us t e to the 3t. This is another solution. And now we have enough for our general solution. So y of t equals c1 e to the 3t plus c2 t e to the 3t. And I want to emphasize that this is not the only thing we could have done. Again, instead of, so this particular function here corresponded to take c to, let's get this to work, c to be 0, c to be 1 and d to be 0, but we could have picked pretty much anything else. We could have made this 1/2 and 1/2, or anything else we wanted to, and that would give us the solution. So we picked the easy one, and that gave us our second solution. And now that we have two solutions, we have our general solution. And every single solution to this equation can be written like this for some value of c1 and c2. Okay, so the last example of this lecture is one that you likely saw coming. What if you have a differential equation like this? And again, p and q are constants. And so we assume the solution is an exponential. We plug it back in, and that characteristic equation we get, that polynomial in R, has two roots, but they're not real. They're complex numbers. Let's say a plus and minus bi. So in other words, we guess that y of t is e to the rt. We plug this in, and we get e to the rt times r squared plus p r plus q equals 0. And we get rid of that. And this equation has complex roots. What then? Well, we still have two solutions. So as before, we have two solutions. We have y1 of t equals e to the a plus bi times t. I should put parentheses there. And we have another solution, y2 of t, that's supposed to be a 2, is e to the a minus bi times t. And yes, that means the general solution, we've done nothing wrong, the general solution is c1 e to the a plus bi times t plus c2 e to the a minus bi times t. That is, I guess I forgot to write y of t, but I guess you know that's y of t. You know, I'll write it here. So this is y of t. So yes, that is correct. But there's a better way to do this, and that's the topic of this slide. Why is there a better way? Well, what does this function look like? E to the a plus bit. That's a complex exponential. It's not clear how to graph something like that. And in general, it's good to avoid imaginary numbers if we can help it. So, so what we'll do is we'll start with this solution, with this equation, and I'll show you a better way to write the general solution. This is going to involve some complex numbers, some things that you are likely rusty with, you haven't seen in a while, and maybe one or two things that you actually haven't seen before. But for now, I'm just going to finish this slide, and then on the last slide of this lecture, I'm going to go over complex numbers as a review, in case you are rusty. Okay, so as I said, there's a better way to write this general solution, and it all depends on something that's called Euler's formula. Either Euler's formula or Euler's equation. And this is that e to the I theta, for any theta, is equal to cosine of theta, it's supposed to be a cosine, plus I sine of theta. And this looks almost too good to be true. It looks sort of magical. Like, how could something like that be true? And why is something like that true? And it's actually fairly straightforward if you look at the complex plane. So let's draw the unit circle here. So this is the real axis. This is the imaginary axis. And this is the number 1. This is I. This is -1. And this down here is -I. So let's take a point on the unit circle with angle theta. This is e to the I theta. That's just the polar form of this complex number. Now, every complex number can be written, well, in polar form, where it's, again, we'll talk about this more in the next slide. So actually, yeah, I'll hold off on that. But this complex number, let's look at this triangle, the base and the height of this triangle. This is a right triangle. And we know from basic high school trig that this length is cosine, do that again, cosine of theta. And again, that's just high school trig. The hypotenuse here is 1. So cosine is adjacent over hypotenuse. And this length here, right like this length is sine of theta. So this complex number up here, called z, or e to the I theta, we can always write it as a plus bi, the real part plus the I times the imaginary part. So that this is cosine of theta plus I sine of theta. Again, the real part, the x direction, plus I times the imaginary part. Sometimes this whole thing is called the imaginary part. Actually, I think usually it is, which is the height. Okay, so that's Euler's equation. Something else about complex numbers you should know is that cosine for any angle or any complex number theta, or any number theta, cosine of theta, actually I should or cosine of negative theta is equal to cosine of theta, and sine of negative theta is equal to negative sine of theta. So why is this? Well, if this angle is theta, then negative theta is this angle down here, negative theta. So this number, this complex number, is e to the negative I times theta, and it's the same x value, the same real part, cosine of theta, because again the same x value, but the y value now is negative. So cosine of theta minus I sine of theta. Because again, to summarize, the difference between theta and negative theta is a reflection across the real axis that does not change the x value, that does not change the cosine value, but it flips the SIGN of the imaginary value. Okay, so given this, let's rewrite our solutions y1 and y2 using Euler's equation. So actually, I'm going to use blue for this. So y1 of t is e to the a plus b, plus bi times t, which is, I'm going to use laws of exponents to write this as e to the a t times e to the I bt. And now I'm going to write that using Euler's equation. So this is e to the a t times cosine of bt plus I sine of bt. Okay, and then y2 of t is e to the a minus bi t, and that is e to the a t times e to the negative I bt, and that is equal to e to the a t times cosine of negative bt plus I of sine of negative bt. And now I'm going to use these two rules. This negative sign gets absorbed into the cosine and becomes positive, and this negative sign pulls out and becomes negative. In other words, this is e to the a t times cosine of bt minus I sine of bt. I don't know why I'm having trouble with my stylus right now. Hopefully it'll get better. Okay, so now we have two solutions, y1 and y2. And this equation, our ODE up here, is homogeneous. It's linear and homogeneous, so that means if we have two solutions, we can add them together and we still get a solution. Or we can subtract them and we get a solution. Or we can multiply one of these by a scalar and we still get a solution. We can take any number, we can take C1 of these and C2 of these and we still get a solution. And that's what our general solution is. So what happens if we add these together? Let's add these up. So this plus this, notice that the signs will cancel and we get 2 e to the at times cosine. It's this term plus that term. So let's do that. So let's take y1 of t plus y2 of t, and actually instead of adding them up, let's add them up and multiply by 1/2. Because if we do that, then we get e to the at times cosine of bt. Now we don't get the 2 out in front. And now let's subtract these as well. y1 minus y2. If we subtract this minus that, the cosines will cancel, and the sines, and what do we get? We get 2 e to the at times I sine of bt. So we get, oh, actually, let me step ahead. Let's take y1 of t minus y2 of t, and let's divide by 2i. If we do that, then we don't have an I out front. So we have e to the at times sine of bt. Okay, so these things, right here, both of these are solutions to our original differential equation. Okay, why is this special? Well, remember, our general solution is a 2-parameter family of solutions. All we need to find are some 2 functions that satisfy this that are not scalar multiples. Well, here's one, y1, here's another one, and here's 2 more. So our general solution can be formed with any 2 of these 4 functions. Originally we took y1 and y2, c1y1 plus c2y2. If you want to, I don't know why you would want to, but you could take this function and this function right here, and you could use those to form your general solution. That'd be kind of weird to mix the complex exponential and this cosine times an exponential. You could do it. But instead, let's use these 2. If we use these 2 functions, then we don't have any i's in the solution. That's pretty desirable. So, so the general solution. Let's write this down. The general solution is y of t can be written as, well, I've used C1 and I've used C2 up here, so I'm going to use capital A and capital B as constants. So I'm going to use A times big A times e to the little at times cosine of bt plus capital B times e to the at times sine of bt. And if I want to, I can factor out, I don't have to, but I can factor out this exponential, and I can write this as e to the at times a times cosine of bt plus capital B sine of little bt. And this is our general solution. And later we'll see how we can actually rewrite this as a single, as a single sine or cosine wave that's shifted with a different amplitude. But that's going to be later in this chapter. For now, one of the things you may be asking is, well, is this general solution, is it the same as this? I mean, here is our other general solution right here. We have 2 of them. Are these actually the same thing? Do they represent the same family of functions? And answer is yes, they do. So these things are actually the same. It's not at all clear. But if we allow our constants C1, C2, or A and B to be any complex number, then these are the same set of solutions. And you can see a little bit. This, given this, so what we did in summary is, given this here, for the specific values of C1 and C2 being 1/2, we got this function. And if C1 was And if C1 and C2 were 1 over 2i and negative 1 over 2i, then we got this function. So these things are exactly the same, but if you want full credit on homework and on exams, I want you to write your solutions using exponentials and sine and cosine waves, not with complex exponentials like this. And not only am I asking you this for your homework, but realistically, if you're working in some sort of lab or in real life, you are going to want your solutions to be something like this, functions that you can graph and you can plot, rather than these mysterious complex exponentials. Okay, so as promised, I will finish this lecture with a basic review of complex numbers, and some of this is stuff you know, but probably something here will be new for you. So stick around, I hope. So in the complex plane, let me draw the complex plane, sketch it like we did last time. So this is the real axis, this is the imaginary axis. A complex number like this, let's call it z. We're used to writing it as a plus bi, right? Where a is this length and b is that length. So this is the real part and this is the imaginary part. Well, we can also write it in polar coordinates. We can instead of these two parameters a and b that we use to represent it, we can think of it, it's also determined by theta and the radius r. This is called polar form. So in this case, if this is the, let me draw the unit circle now. Recall that any point on the unit circle is always e to the I theta. So if this is theta, then the corresponding, if the angle is theta, then this point is e to the I theta. So this point up here is that scaled by r. So this is r times e to the I theta, which, let's do our trigonometry that we did before. This is the, this right here is basic high school trig, is r cosine of theta, and this height is r sine of theta. So in other words, this is just r cosine of theta plus I times r sine of theta. So differently, a is equal to, let's write it like this, a is equal to r cosine of theta, and b up here is equal to r sine theta. So as before, from this, it's easy to see. So from last time, note or recall that cosine of negative theta is always equal to cosine of theta, and sine of negative theta is equal to negative sine of theta. And again, that's because the difference between theta and negative theta is just the reflection across the real axis. Negative theta is going to be the angle that's down here. Okay, so Euler's formula. Let's also recall Euler's formula. Euler's formula is e to the I times theta equals cosine of theta plus I sine of theta. That's something you should know, you should memorize. It's remarkable. Why is it remarkable? Well, it means, well, this with this together means several things. So neat facts. That e to the I times theta is cosine, well, I'm going to rewrite the same thing, cosine of theta plus I sine of theta, but I'm also going to write e to the minus I theta is cosine of theta minus I sine of theta. So if we put these two things together, we can do a similar trick to what we did last time. If we add these together, so add these together and divide by 2, well, if we add these together, the sines cancel and we get 2 cosine. So what that means is e to the I theta plus e to the minus I theta times divided by 2 or times 1/2, that is cosine of theta. All right? Add these two things together and divide by 2, and these cancel, and you get cosine of theta. And that's actually supposed to be not an equal sign, that's supposed to be implies. And if we add these things together, or let's subtract these. Let's subtract these two things. So now the cosines cancel, and we get 2I sine of theta. So if we subtract them and divide by 2I, e to the negative I theta, 1 over 2I, now we get sine of theta. So this is something that I bet not all of you have seen, that cosine, the cosine and sine functions can actually be written using complex exponentials in a really simple function, in a really simple way like this. Okay, so here's something else that's neat. Also, what happens if we take e? So let's use this formula: e to the I times pi. Let's set pi equal to theta. So let's do that two different ways. So e to the I times pi. Well, geometrically, that's the complex number. E to the I theta is always on the unit circle, so e to the I times pi is the complex number that is right there. And that is -1, right? It's on the real axis. So e to the I theta equals -1, and that's actually a very remarkable formula. Identity, I guess. Because here you have three sort of magical numbers that come up all throughout mathematics. You know, you've heard all the time that e comes up in nature. E is a special irrational number. So is pi. The ancient Greeks knew it. And then I is the fundamental imaginary number, I. And if you take e and raise it to the I times theta, out pops -1. And that's pretty remarkable. So let me finish by saying a few things about Taylor series. I'm not going to quiz you on this, but I think it'll help you see a new connection, or I guess a new way why Euler's formula is true. Because right now I've sort of just told it to you and said, believe me. And you can do it. So using Taylor series, you may remember from Calc 2, Taylor series. Series. Remember that e to the I times, I'm going to use t now instead of theta. E to the it is I equals 0 up to infinity. So here's the Taylor series for e to the I. T is t to the n over n factorial. Remember that? Do you remember the Taylor series for sine and cosine? I'm going to do them in blue now. How do I want it? I guess this one I can do right here. Sine of theta is so it's Taylor series of sine of theta. Actually, now I have to use theta because I've been saying, let's change this into theta. Let's make this a theta. Let's make that a theta. So, how do I want to write this? Yeah, I'm going to go down here actually now, and I'm going to say that e to the I times theta equals 1 plus, actually, hold off on this for a second. Let me finish what I'm doing. So you may remember from Calc 2 that the Taylor series for e to the I theta is, that's terrible looking theta, but I guess it'll have, you know what it is, it's theta. So it's this series that has every single power of theta, and it has a factorial on the bottom, and the sine series is just the even terms, but you alternate in, sorry, just the odd terms, but you alternate in sine, S-I-G-N. So it's actually, it's -1 to the n times theta to the 2n plus 1 over 2n plus 1 factorial, and cosine, this series is the same thing, but it's with the evens instead of the odd terms. So this is n equals 0 to infinity of -1 n times theta to the 2n over 2n factorial. So if you're like me, I don't really like these closed formulas very well. I like to just write out the first 8 terms. And if you do that, e to the I theta, now remember, I squared is -1, and I to the 4th is +1, and I to the, so let me just remind you that I squared is -1, I cubed is -I, and I to the 4th is -1 squared, so is +1. So e to the I theta is 1 plus I times theta plus I times theta squared over 2 factorial. This is just -1 times theta squared plus I times theta cubed over 3 factorial plus I times theta to the 4th over 4. I'm going to do a couple more of these, plus I times theta to the 5th over 5 factorial plus I times theta to the 6th over 6 factorial plus I times theta to the 7th over 7 factorial plus I times theta to the 8th over 8 factorial plus etc. Okay, so let's do the cosine series. So cosine of theta is, remember, it's just the even terms of this, but the signs flip, so it's going to be 1, oh that's, sorry, let's 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta 6th over 6 factorial plus theta to the 8th over 8 factorial plus minus etc. And let's take the sine series, multiply by I. The sine series is the same thing. You get the odd terms. So I times sine theta is I times theta minus I times theta cubed over 3 factorial plus I times theta to the 5th over 5 factorial minus I times theta to the 7th over 7 factorial plus minus etc. And now look what you get when you add these things up. You may notice that, so here I have a negative theta squared. These two terms are the same because I squared is -1. Here, these terms are the same because I to the fourth is positive 1. These are the same because I to the sixth is I squared, because I to the fourth is 1, which is negative 1, and so forth. Similarly, these, you can check that these terms are the same, that's obvious. These terms are the same, these terms are the same, and so forth. And so what we get is we get that e to the I theta, just based on its Taylor series. I know you're probably a little bit rusty on it, that's okay, I won't quiz you on it. E to the I theta, this line is just that line plus that line. And that is one way to show why Euler's formula is in fact true.